Hello everyone and welcome back. This is Professor Vlachos. Today we are going to discuss about clustering. So far we have covered regression and classification. In regression we try to predict a real number given a set of features, let's say the price of a house. In classification we are trying to predict a category or a class given a certain feature or set of features. For example, something that we would like to predict is given someone's income, given someone's age, number of kids, we try to predict if we should give a loan to this person or not. Both regression and classification are called supervised learning because we give the labels y, we give the features x, so x are the features, but we also give the labels y. So we give some training example.
Now we move into clustering, which is an instance of unsupervised learning.
Here we don't have any labels. Someone has not told us if something is good or bad. We try to make sense based on the structure of the data. So based on what we see, if something looks similar to something else, then we can make some deductions about this. In clustering, we try to find groups of points, let's say to automatically group clusters into high, low, and medium income. Therefore, here we train only on the x, only on the features.
Under unsupervised learning, we also have dimensionality reduction and association rule mining.
So what is clustering? The goal of clustering is to organize the data into classes so that there is high intra-class similarity. So if I have a certain class, I want this to be very similar to each other, assuming that I plot everything on 2D. And I want low inter-class similarity. So between these, I want all this distance to be far. So between the cluster, what I identify as cluster, I want the distance to be low, same here. But between the two classes, 1 and 2, or the two groups, I want the distance to be high, or the similarity to be low. Let's see an example. So imagine that I have in my computer images. I just have images of sunset and images of sea, and they are mixed with each other. So the outcome of the clustering would give two clusters, one with the images of sunset and one with the images of sea. This is of course the ideal case. Clustering probably never will give the correct clustering if we don't give labels as well. But if we start giving some tags, maybe using some classification process we can do this. But you should not expect that the clustering is going to give perfect results, but it's a good starting point. What did we have so far based, let's say, in classification? We had the features, so these two were the features of some person, of some object, of some customer. And then we had the label. Yes, it's safe to give the loan. No, it's not safe to give the loan. So this column is the label. Yes and no in this case. It might have been more classes. And based on this, we learned this division that, okay, these are the good loans over here, and these are the bad loans over here. Now in clustering, what is the difference? In clustering, we don't have this column anymore, so forget about this column. We just have the features, and we don't know if they are good or if they are bad. So what's the best that we can do here? We can see, okay, some objects, they look like they are similar, and we can do this. We can try to understand what is the structure in this unlabeled data, right? So all are gray now. We don't have blue and red. Everything is gray. So let's say using some procedure, we managed to say, okay, these more or less look similar. And let's say this we call class A, and this we call class B, so we expect most of them to be non-safe loans. So what happens in this case? What we can do is we can label them. So we can say, okay, everything in this class is going to be blue and everything in this class is going to be red. Right? So before we had gray points, we did clustering, and then everything here is going to be red, and everything here is going to be blue. Right? It's blue as well. Right? So this is how we end up here. We label and say everything, but we don't label one by one. So we can say everything that belongs into this cluster is of class A, and everything that belongs into this class B is a non-safe loan. But recall here that this was a blue point before originally. So we had the line somewhere here. So this was a blue point, right? If we had the original label, we would have seen that this is blue. So doing the clustering is not as accurate as getting the label data, which is of course to be understood. There is no human intervention here to say that something is blue and something is red. Based on how the points are projected into this space, into the feature space, we are trying to understand what is happening with them. Are they good or are they bad? Now, if a new point comes, what can we say? Oh, this is more close to the red cluster, or this belongs inside the red cluster. So we are going to classify it as a safe loan. So this is a way of doing classification using clustering. We annotate the cluster, so everything that belongs into this cluster becomes of the same class, of the same label. And then if something is closer to cluster A or to cluster B, then we classify it accordingly. So we can use it for classification. We can also use it for anomaly detection or for outlier detection. So small clusters that are distant to anything else, they can be classified as something that, something happened or we have an incorrect value. There was some error in the sensor that collected the data, or maybe someone typed the wrong value. So this red point here, maybe it's a potential outlier. How we could identify this? Assume we had 3 clusters, or we try to discover 3 clusters, something that is very distant from the other 2 big clusters, maybe it is a potential outlier. Other applications of clustering, simplification. If we do the clustering, what are we learning? What we are learning is we can replace all of these, let's say, the safe loans with the average of the central, let's say, point to all of the points that belong to the blue cluster. So the center of its cluster represents the average of all the data points of that cluster. So this is the prototypical safe customer. So it should be more or less here. So it should have more or less a credit score of 740 and an income of around 300K. And the prototypical or the average customer that does not get the loan has 150K and has a rating, credit rating of, let's say, slightly below 700. Okay, so this is the cluster center. The cluster center is nothing more than the average of the x and the y coordinates in this case. Or the average, if you have more features, it's the average across every feature. There are 2 main classes of clustering, partitional clustering, and a very significant, very important, very widely used instance of it is k-means, where we try different partitions of the data and we keep the one that gives the best fit based on some criterion that we use. So this is partitional. So we try different ones and we keep the one that is the best. So you can imagine that there is some kind of optimization happening here based on some fit function. The same thing that we did for classification, the same thing that we did for regression. In hierarchical clustering, we create a hierarchical decomposition of the objects using some distance function. typically we start from the bottom and we start merging objects until we end up with one cluster in the beginning. We'll see more details about this very soon. So first we are going to examine the partitional clustering or k-means. Of course, the clustering outcome depends highly on the similarity or distance measure that is going to be used, what we consider similar or what we consider distant. Again, the notion of similarity and distance, they are inverse, right? They are inversely proportional. If something has high distance, it has low similarity. If it has low similarity, it has high distance. So what distance measures have we examined so far? We have examined, of course, the Euclidean distance, which we also called L2, and we also examined the Manhattan distance, or block distance, which we called L1. But of course, you should remember that similarity is subjective. So if I show you these two pictures, these two images, so this is 1 and this is 2, would you say that it's similar or not? You understanding that the right one is a dog and the left one is a person, you would say no, they are not similar, but imagine that we had used the color as the similarity measure between images. Remember the case that we tried to identify if something was a sunset or something was a sea. So we could have used the color, blue versus red or orange. So in this case, if we had used the color as the similarity measure or as the distance measure, we would have found that these two images, they are highly similar. Therefore, you should remember that based on the application, you should consider or reconsider what you are going to use as distance or similarity. Now, for partitional clustering, this is non-hierarchical, and each instance or each object is placed in exactly one non-overlapping cluster. Non-overlapping means that each cluster is not going to share objects with any other cluster. They are going to be distinct. And since we only output one set of clusters, the user has to input the desired number of clusters, which is of course unknown, unless you have some underlying information which tells you, okay, maybe I have 5 clusters in my data, 5 groups of people, and then you put or 5 or 6 some close by number. But typically we have to try many numbers of k and see which one to pick, and we are going to see a technique for doing that. We examined this scenario in the introduction as well, just to illustrate clustering. So imagine that you own all of these boulangeries. So each dot here is a boulangerie in Lausanne. But you can only afford 2 distribution centers in Lausanne to supply the raw material for these boulangeries. So where are you going to build these 2 distribution centers? Are you going to build them here and here? This does not appear to be a good solution. But putting them in the center of these clusters of shops most likely looks like a better solution. So how can you formalize, how can you express in an equation, in some mathematical form, that this, so having 1 here and 2 here for your distribution centers, is a better solution? We need a single number that we can compare different solutions and we can say, okay, this one is better than the other. So we need a fit function. Recall for regression, we had the residual sum of squares. So if this is the function that approximates these data points, we summed up the distance to this line, the square. And the cost function is somehow here. It's the same in this case as well. So in this case, if this is one center and this is another center, which we call M1 and M2, The cost function, which we call inertia, is the sum of intra-cluster distances. So all the points that are closer to this center, they belong to this cluster. So all these points, because they are closer to M1, they belong to this cluster. So what we do is, in order to find the inertia, is we sum up the squares of these distances, all right? So this is the xn, we take the difference and we square it, we sum them up. Okay, this R function is simply saying it's 1 if it belongs to a cluster or not, so you can forget about it if you want. All right, this is just an indicator function. So we sum up for every cluster, and then we sum up for all the clusters here. This is for all the points, and this is for all the clusters. So for every cluster and for every point, we sum up these differences. So obviously, if the center was chosen to be here, you can see that the distances are much higher. So this is a better fit. These are better centers. So essentially, the issue of doing clustering resorts to finding the centers. If I want k clusters, I have to find k cluster centers, and this would be enough. So this is the k-means algorithm that does that. First, we decide on a value of k, or you can try many of them. You initialize these centers randomly, so you place them somewhere randomly, let's say k equals 2. You decide your points. Where do they belong? Are they closer to this point or to this point? And then we assign it. So let's say we assign this here and this here. Then we re-estimate the cluster centers, assuming the memberships are correct, by averaging again. We'll see this using some example. And if none of the objects changed membership in the last iteration, then we exit. Otherwise, we repeat this. So we re-average, we recalculate the cluster centers, and we go on like this until stability. An example. Algorithm K means distance metric, we choose the Euclidean distance. We have these data points, these two-dimensional data points that we would like to cluster. And assume that as K, we pick the number 3. We said this resorts to finding K centers. So these K centers, we pick them randomly somewhere here. 1, 2, 3. Then what do we do? For every point, we find, is it closer to which center? To this, or to this? Now we see that this is closer to this point. So this data point is going to belong into the center, into the cluster, which has this one as the center. Right? So everything that belongs in here, and let me take a different color. So everything that belongs here is going to be a green data point. Everything that belongs here is going to be a red data point, so it's going to belong to this cluster, and everything that belongs here is going to be an orange data point. Now, in the next step, what we do? We recalculate the new center. So we use these data points, 1, 2, 3, 4, all these data points that belong to this cluster, and what is the new center? Most likely it's going to be somewhere here. Right, so it's going to move towards this way. The cluster center towards this way here and towards this way in this example. All right, then we repeat which one is closer to the... So this point belonged here before, but now maybe it belongs here in this case. All right, so now it becomes red. So now we have this kind of clustering. And then we repeat until stability. So we go on, we go on, we go on. If you want to play with k-means, this is a very nice visual example. So just click on this link. First, you pick the number of clusters. You generate some data points. And then you click cluster to see the steps. You can click cluster several times to start with different centers. Okay, so this is a nice illustration in JavaScript to understand how k-means works, in addition to this example that we have seen here.
Let's see in action what happens when we have 3 clusters here. We click generate, we generate 100 points which belong to 3 clusters, and then when we click cluster, it will generate 3 random centers, and it will start moving these centers so that it optimizes, that it minimizes the cost that the k-means function has. So we start with this, red, green, and blue, and we see in a few iterations it manages to find actually pretty good clusters. Let's click again on the generate. Now we have 1, 2, 3 clusters. Let's see how it works now. Okay, it's pretty good, they move pretty well. Now let's generate another one. So these are the original random clusters, random centers. Let's see now. Okay, it moves, etc. So in all of the cases it worked pretty well, but you are going to find some cases where the clusters may be slightly overlapping, so it is not going to work so well. Let's see here, for example. Okay, in general, you can see that it works relatively well.
So what are the pros and the cons of k-means? The pros is that it scales well with the dataset size. The negatives is that we need to know the number of clusters, or we need to try many of them. It may not be suitable to discover non-circular shapes. We'll see an example of this later. So it only discovers blobs which are kind of round. If you have things which are concentric, so imagine that you have these data points and these data points. So if you do it with k-means, half of them will belong to this cluster and half will belong to the other cluster. So if the shapes that you want to describe, they are not circular or elliptical into some shape, you cannot do it very easily, or if they are not well separated. And of course, it is applicable when the average is defined. So if you have categorical data, okay, you have to see, okay, what is the average in this case? So k-means works well for numeric data. If you have categorical data, then you may have to think a little bit what the average represents. Again, we said it favors spherical clusters. So imagine we have these data points here, which if you plot it, it corresponds to a smiley. How would you cluster this? You could say, okay, we have one cluster here, one cluster here, one cluster here, and one cluster is this outside data. So we have 1, 2, 3, 4 clusters. If I put 4 in the k-means, it's going to cluster it like this. 1, 2, 3, 4. So it assumes that everything is kind of a little bit spherical here, right? It's not going to work in this case. How do you find the number of clusters? This is in general an unsolved problem. There are many approximate methods. This slide is going to show you an example of how to do it. Imagine you have these 2 blobs of data points. You can see here more or less that these belong to 2 clusters. How can you do it? You start with k equals 1. So the objective function, the inertia that we said, so the distance, the sum of squares of all of these points to this, let's say that it is 1050. You try with k equals 2. Then you see that the objective function drops to 103. Then you try with 3 clusters. You see that it drops to 93. Of course, the more points that you use, the lower the inertia is going to be, the more clusters that you use. But you can see that you have a very, very big drop here. So this technique is called the elbow technique. So as soon as you see some elbow in your data, this suggests that most likely this is a good number of clusters. So the k equals 2. Right? This is called the knee or elbow finding method. Of course, the results that you get with real data, they are not as clear-cut as this toy example, where we had a very clear separation between the classes. But this is something that you should consider in order to find at least a good range of clusters. Clustering can be used very extensively for categorizing or for grouping customers. You can see some examples by following these links. So these are good examples. I urge you to follow them. You can spend 5 minutes or so to peruse through these examples. All right, these two, they are the same example. This is slightly different. But all of these, they perform customer segmentation. Now let's move into hierarchical clustering. Why do we need, first of all, hierarchical clustering? Because it addresses two of the main shortcomings of partitional clustering, of k-means. You don't have to specify the number of clusters. In hierarchical clustering, essentially, you try all of them and you group them hierarchically. And you can detect more complex shapes, which is something that is probably more important. You can detect things that they are not necessarily circular, so they can have any type of shape. Additional advantages, they can be visualized using dendrograms, which is a nice way to see the clusters at different resolutions. All right, this is a customer segmentation dendrogram. And hierarchical clustering is going to work with any type of distance or similarity measure, whereas k-means inherently assumes that you use Euclidean distance. Dendrograms have been used in many disciplines. In evolutionary biology, as you can see here, to determine, the similarity between the different species. And here the similarity is typically done on a genomic level. In culture studies, this is to find similarity between different shields. In religious studies, to see how similar or dissimilar the different religions are. And even to do similarity on a language level. So here we do hierarchical clustering on names. Here we use the edit distance, which is a distance between strings. So the edit distance essentially says how many changes you have to make to one string to transform it into the other. Here we can see that Piotr and Piotr, they are very similar. Petros, Pietro, so Petros is Greek, Pietro Italian, Pedro is Spanish, all these are similar. Pekka, Pedar, which are more from the northern countries. We have two types of hierarchical clustering, a divisive one where we start from the top and we divide the clusters, or we have an agglomerative one, which is called bottom-up, where each point is its own cluster in the beginning, and then we start merging until we are left with one cluster. Let's see a walkthrough of the bottom-up hierarchical clustering. Imagine that we have our elves and our hobbits from Lord of the Rings. And we would like to cluster them based on two features, based on their height and based on their length of their hair. So you all know that the elves, they are tall and they also have long hair, whereas the hobbits, they are short and they have, let's say, medium-sized length of hair. So if we plot them here, these are the hobbits and these are the elves up here, we are going to perform clustering on them and see if we end up with the correct clustering. So how does hierarchical clustering start? It starts by computing all the pairwise distances between the objects that we have here, between the elves and the hobbits. All right, so all the pairwise distances here we have, let's say, the L2 distance, the Euclidean distance between these data points. All right, so we can see that Arwen and Lord Elrond, they have a distance of 57, whereas Arwen and Pippin, they have a distance of 145, so they are more dissimilar in the 2D space. So we start with this, and then what do we say? We say each object belongs in its own cluster, so each object belongs, so this is the clustering outcome. Clustering. This is here what we see, and this is how they are visualized on the 2D. So in the beginning, every point belongs in its own cluster. Now we find the pair the pair that has the smallest distance. So the pair that is the most similar. Which one is it? It is this one, and as you can see, this is the least distance between them. So we merge these two. All right, so these two are merged. And the distances to the other points, it is replaced. And then we continue. What is the next most similar distance? The most similar pair of objects, it is this and this. These two are merged and they belong to the same cluster. Which is the more similar, the next one? It is this and this cluster. And then we continue. The next step, this is merged with this cluster. And finally, in the final step, we have one cluster, so everything belongs to the same cluster, and all the data points are merged. They are fused together. So how do you get the clusters here? Here you can cut at any point. So you can cut here, you can cut here, but here you can see that there is a very big distance between these two clusters. All right, so the height of this dendrogram corresponds to the distance between the clusters that are merged. All right, so here you see a very big distance between them. So what you can say is most likely, oh, I have two clusters. So I have this and this cluster. We can pick any distance function to define the distance between the data objects, Euclidean, cosine distance, etc. We didn't cover, I think, the cosine, but you can look it up. The question here is, how do we define the distance between sets of objects? Between objects, we can define the distance. So between clusters or between a point and a cluster, what is the actual distance? There are many ways to define this. And based on how the distance between clusters is defined, we have different types of hierarchical clustering. We have the single linkage, or the nearest neighbor. So if these two are clusters, the distance between them is the distance between the closest points. So these two are the closest points. Therefore, this minimum distance is considered as the distance between these two clusters. Right? Not the distance between the centers, but the distance between the closest points. This is the single linkage. The complete linkage is the opposite, as the distance between clusters is considered the maximum distance between every of the data points that belong into these two clusters. This is going to force clusters to be more separated, whereas the previous case, the single linkage, is going to form elongated clusters. You can also take the average. So the average of all the pairwise distances between the data points on the two clusters is the average linkage method. And there is also another method, which is the Ward's distance. In this method, distance is the variance of the merged clusters. So if these two were merged, so if cluster 1 and cluster 2 were to be merged, what would happen? The center would have been this one. So what is the variance of the data points? The variance is essentially the distance to any of these data points. And if we kept them separately, what would be the variance? This would be the center, and this, the sum of all of this, would be the variance, all right? The squared distance for all of them, the average of them. All right, so we see, is the variance smaller or bigger if we merge these two clusters? And this is how we try to merge clusters. So we merge clusters that lead to the smallest variance. Hierarchical clustering in sklearn, it's very simple. It is just one function. Okay, so this agglomerative clustering. It takes different parameters. The distance metric, we examined here L2 and L1. You can also pick other functions, cosine, eddy distance, earth mover distance. This is a little bit more complex. You can click on the links if you want to see a definition in Wikipedia. For the linkage function, so how clusters are merged, or points and clusters, we have single linkage, complete linkage, average, and words. A final example to illustrate the difference between k-means and hierarchical clustering. So this is for 1, 2, 3, 4, 5 datasets. If I pick k-means, where the k varies, so the k is 2 here, so it is the same as the number of clusters that normally we see as humans. So it would be 2 here, it would be 3 here, 3 here, and 3 here. We see that k-means is only successful in this case, where we actually have nice spherical clusters which are well separated. In most of the other cases, for example here, we would have classified maybe this, this, and that. But you see that it favors, distinct regions like this, this, and this. Again, the same in this case. The same in this, the same in this, if we pick k equals 2. Now, if we do it with hierarchical clustering, we can see that in almost all the cases, maybe except for this case here, it finds the correct clusters, more or less. At the bottom here, you see the time that it took. So what you would notice is that hierarchical clustering is more accurate, but it takes much more time. So this is much more costly too. Right, so this is something that you should remember. If you have very large datasets to cluster, most likely you would like to do k-means rather than hierarchical clustering. So this is the runtime complexity of k-means. If you are not a computer scientist, probably you don't understand what this O notation means. But what it means is that it depends on the number of clusters, on the iterations, and the number of objects that we have. So it's linear to all of these three, and hierarchical clustering is at least quadratic. So it depends on the square of the number of objects that you have. So it's going to explode the complexity if you have a lot of objects. Typically, you cannot do hierarchical clustering for more than 10,000 objects. It's going to require too much memory, too much CPU time. Because you have to compute this pairwise distance matrix, whereas for k-means you don't have to do that. Therefore, hierarchical clustering is very visual. It's very good for exploratory data analysis. It provides a hierarchical organization of your data. There is no need to determine a priori the number of clusters, and it can detect arbitrarily shaped clusters. So this is the most important thing that you should remember. The negatives is that it has very large complexity. Typically, you're not going to use it if you have a few thousand points or more than 10 or 20,000 points. Therefore, what we cover today is k-means, so partitional clustering. This is partitional clustering. We have covered hierarchical clustering and the various variants, single, complete, average, linkage, and also the words. This kind of sums up what we are going to discuss about clustering. In the lab, we are going to see some more examples, some hands-on examples about how to do hierarchical and k-means clustering using sklearn.